Yep, that should be fine. Right, I'm not sure. Let's continue. Value expressions. So I did not change anything from yesterday. I considered changing something, but then I realized that it might be better to continue just as is. I don't have enough time to change the stuff that I wanted to change, unfortunately. But I'm going to continue just as is. So, value expressions are used in a variety of contexts, such as the target list or select command as new command values and insert or update, or in search conditions in a number of commands. The result of a value expression is sometimes called a scalar, to distinguish from the result of a table expression, which is a table. Value expressions are therefore also called scalar expressions, or even simply expressions. The expression syntax allows the calculation of values from primitive parts using algorithm, a logical set, and other operations. Value expression is one of the following: constant, column reference, a positional parameter reference in the body of a function definition or prepared statement, and or a subscripted expression, a field selection expression, an operator invocation, a function call, an aggregate expression, a window function call, a typecast, a collation expression, a scalar subquery, an array constructor, a row constructor, another value expression parenthesis used to group sub-expressions and override precedence. So that was a lot. In addition to these lists, there are a number of constructs that can be classified as an expression but do not follow any general syntax rules. These generally have the semantics of a function or operator and are explained in the appropriate location in Chapter 9. An example is the is-null clause. We have already discussed constants in section 4.1.2. The following sections discuss the remaining options. Column references. A column can be referenced in the form correlation.column name. Correlation is the name of the table, possibly qualified with a schema name or an alias for the table defined by means of a from clause. The correlation name and separating dot can be omitted if the column name is unique across all tables being used in the current query. A positional parameter reference is used to indicate a value that is supplied externally to a SQL statement. Parameters are used in SQL function definitions and in prepared queries. Some client libraries also support specifying data values separately from the SQL command string, in which case parameters are used to refer to the out-of-line data values. The form of a parameter reference is $number. For example, consider the following definition of a function department as create function department, which takes text, returns department as $. Select star from a department where name is equal to $1, so this is one we have this, right? Language SQL. Here $1 references the value of the first function argument whenever the function is invoked. Subscripts. If an expression yields a value of an array type, then a specific element of the array value can be extracted by writing expression subscript, or multiple adjacent elements. An array slice can be extracted by writing expression or expression of lower subscript to upper subscript. So you have array indexing. Here the brackets are meant to appear literally. Each subscript is itself an expression which will be rounded to the next nearest integer value. In general, the array expression must be parenthesized, but the parentheses can be omitted when the expression is to be subscripted is just a column reference or a positional parameter. Also, multiple subscripts can be concatenated when the original array is multidimensional. For example, myTable.array column 4, myTable. Okay. So you have a 2D, 3D array, you can do this. So $1 and 42, 10 to 42. You have an array function which returns an array, and then you have 42. The parentheses in the last example are required. See section 8.15 for more about arrays. If an expression yields a value of composite type, row type, then a specific field of the row can be extracted by writing expression.field. In general, the row expression must be parenthesized, but the parentheses can be omitted when the expression to be selected from is just a table reference or a positional parameter. For example, myTable.column, $1 some column, some function dot column 3. This is the table reference. So you're selecting the appropriate column. That makes sense, doesn't it? The parentheses are required here to show that composite call is a column name, not a table name, and that my table is a table name, not a schema name in the second case. You can ask for all fields of a composite value by writing a dot star. This notation behaves differently depending upon context. See section 8.16.5 for details. Operator invocations. There are two possible syntaxes for an operator invocation. Expression, operator, expression. Binary infix operator, or operator expression, unary prefix operator, where the operator token follows the syntax rules of 4.1.3 or is one of the keywords and or not, or is a qualified operator with a name in the form operator schema.operator name. Which particular operators exist and whether they're unary or binary depends on what operators have been defined by the system or the user. Chapter 9 describes the built-in operators. Function calls. The syntax for a function call is the name of a function, possibly qualified with a schema name, followed by its argument list enclosed in parentheses. For example, the function computes the square root of 2. The list of built-in functions is in chapter 9. Other functions can be added by the user. When issuing queries in a database where some users may structure other users, observe security precautions from section 10.3 when writing function calls. The arguments can optionally have names attached. Keyword arguments. 4.3 for details. Note, a function that takes a single argument of composite type can optionally be called using the field selection syntax, and conversely, field selection can be written in functional style. That is, the notations of call, table, and table.call are interchangeable. This behavior is not SQL standard, but is provided by Postgres because it allows user functions to emulate computed fields. For more information, this section, right? Aggregate expressions. An aggregate expression represents the application of an aggregate function across the rows selected by query. An aggregate function reduces multiple inputs to a single output value, such as the sum or the average of the inputs. The syntax of an aggregate expression is aggregate expression, order by clause, filter, where clause. Aggregate name, nice, all distinct, star, filter, expression. Aggregate name is a previously defined aggregate, possibly qualified with a schema name. An expression is any value expression that does not itself contain an aggregate expression or a window function call. The optional order by clause and filter clause are described below. The first form of aggregate expression involves the aggregate ones for each input row. The second form is the same as the first, since all is the default. The fourth form invokes the aggregate once for each input row, since no particular input value is specified. It is generally only useful for the count star aggregate function. The last form is used with ordered set aggregate functions, which are described below. Most aggregate functions ignore null inputs, so that rows in which one or more of the expressions yield null are discarded. This can be assumed to be true, unless otherwise specified for all built-in aggregates. For example, count star yields the total number of input rows. Count F1 yields the number of input rows in which F1 is not null. Since count ignores the nulls, and count distinct F1 yields the number of distinct non-null values of F1. Ordinarily, the input rows are fed to the aggregate function in an unspecified order. In many cases, this does not matter. For example, min produces the same result no matter what order it receives values in. However, some aggregate functions such as array aggregate and string aggregate produce results that depend upon the ordering of the input rows. When using such an aggregate, the optional order by clause can be used to specify the desired ordering. The order by clause has the same syntax as for a query level order by clause as described in 7.5, except its expressions are always just expressions from output column names of numbers. For example, select aggregate function A order by B descending from table. When dealing with multiple argument aggregate functions, note that order by clause goes after all the aggregate arguments. For example, write this: select string aggregate A, comma, order by A from table, not this. Select string A order by A, comma, from table, incorrect. Okay. The latter is syntactically valid, but it represents a call of single argument aggregate function with two order by keys. The second one being rather useless since it's a constant. Distinct is specified in an order in addition to order by clause, then all the order by statement expressions must match regular expression arguments of the aggregate. That is, you cannot sort on an expression that is not included in the distinct list. Note, the ability to specify both distinct and order by in an aggregate function is a PostgreSQL extension. Placing order by within the aggregate's regular argument list, as described so far, is used when ordering the input rows with general purpose and statistical aggregates, for which ordering is optional. There is a subclass of aggregate functions called ordered set aggregates, for which an order by clause is required, usually because the aggregate's computation is only sensible in terms of a specific ordering of its input rows. Typical extensions of ordered set aggregates include rank and percentile calculations. For an ordered set aggregate, the order by clause is written inside within group, as shown in the final syntax alternative above. The expressions in the order by clause are evaluated once per input row, just like regular aggregate functions, sorted as per order by clause's requirements and fed to the aggregate function as input arguments. This is unlike the case for a non-within group order by clause, which is not treated as arguments to the aggregate function. The argument expressions preceding within group, if any, are called direct arguments to distinguish them from the aggregated arguments listed in the order by clause. Unlike regular aggregate arguments, direct arguments are evaluated only once per aggregate call, not once per input row. This means they can contain variables only if those variables are grouped by group by. This restriction is the same as if the direct arguments were not inside an aggregate expression at all. Direct arguments are typically used for things like percentile fractions, which only make sense as a single value per aggregate calculation. The direct argument list can be empty. In this case, just parenthesis, not star, a parenthesis star. Postgres will actually accept either spelling, but only the first way conforms to the SQL standard. An example of an ordered set aggregate call is select percentile cont 0.5 within group order by income from households percentile. Okay, that sort of makes zero sense. I've never used any of this. Select percentile count within group order by income from households, which obtains the 50th percentile or median value of the income column from table households. Here 0.5 is a direct argument. It would make no sense for the percentile fraction to be varying across rows. If filter is specified, then only the input rows for which the filter clause evaluates to true are fed to the aggregate function. Other rows are discarded. For example, count star filter where as filtered from generated series 1 of 10 as si and so far. The predefined aggregate functions are described in 9.21. Other aggregate functions are added by the user. An aggregate expression can only appear in the result of having clause of a select. It is forbidden in other clauses such as where, because those clauses are logically evaluated before the results of aggregates are formed. When an aggregate expression appears in a subquery, the aggregate is normally evaluated over the rows of the subquery, but an exception occurs if the aggregate's arguments and filter clause, if any, contain only outer level variables. The aggregate then belongs to the nearest such outer level and is evaluated over the rows of that query. The aggregate expression as a whole is then an outer reference for the subquery it appears in, and acts as a constant over anyone evaluation of that subquery. The restrictions about appearing only in the result list or having clause applies with respect to the subquery level that the aggregate belongs to. Back. Sorry about that. Cool. Window function calls. A window function call represents the application of an aggregate-like function over some portion of the row selected by a query. Unlike non-window aggregate calls, this is not tied to the grouping of select rows in a single output row. Each row remains separate in the query output. However, the window function has access to all the rows that would be part of the current rows group according to the group's grouping specification. Of the window function call. The syntax of the window function call is one of the followings. Where window definition has the syntax. The optional frame clause can be one of these, where frame start and frame end can be one of these. Undone proceeding, offset this. frame start and frame end can be one of the unbounded preceding, offset preceding, current rows, offset following, and frame exclusion. Here expression represents any value expression that does not itself contain window function calls. A window name is a reference to a named window specification defined in the query's window clause. Alternatively, a full window definition can be given within parentheses using the same syntax as for defining a named window in the window clause. See select reference page over details. It's worth pointing out that over WName is not exactly equivalent to over. The latter implies copying and modifying the window definition and will be rejected if the reference window specification includes a frame clause. The partition by clause groups the rows of the query into partitions, which are processed separately by the window function. Partition by works similarly to a query level group by clause, except that its expressions are always just expressions and cannot be output column names or numbers. Without partition by, all rows produced by the query are treated as a single partition. The order by clause determines the order in which the rows of the partition are processed by the window function call. It works similarly to a query level order by clause, but cannot use output column names or numbers. This is interesting. Where am I? See, select page is worth noting. The partition by clause. Yeah, this all not making sense to me. I'm going to skip this entire section. Window functions. Typecasts. We saw this before. You have two expressions. You have this, or you have this thing. So, when cast is applied to a value expression of a known type, it represents a type name, runtime type conversion. The cast will succeed only if a suitable type conversion operation has been defined. Notice that this is subtly different from the use of cast with constants as shown in section 4.1.2.7. A cast applied to an unadorned string literal represents the initial assignment of a type to a literal constant value, and so it will succeed for any type if the contents of the string literal are acceptable input syntax for the data type. An explicit typecast can be usually omitted if there is no ambiguity as to the type that the value expression must produce. The system will automatically apply a typecast in such cases. However, the automatic casting is done for casts that are marked OK to apply implicitly in the system catalogs. Other casts must be invoked with explicit casting syntax. This restriction is intended to prevent surprising conversions from being applied silently. It is also possible to specify a typecast using a function-like syntax. However, this only works for types whose names are also valid as function names. For example, double precision cannot be used this way, but the equivalent float 8 can. Also, intervals, time and timestamp can be used in this fashion if they are double-quoted because of the syntactic conflicts. Therefore, use of the function-like cast syntax leads to inconsistencies and should possibly be avoided. The function-like syntax is just a function call. When two standard cast function syntaxes are used to do runtime conversion, it will internally invoke a registered function to perform the conversion. By convention, these conversion functions have the same name as the output type, and thus the function-like syntax is nothing more than a direct invocation of the underlying conversion function. Obviously, this is not something that a portable application should rely on. For further details, see create cast. Collation functions are expressions. The collate clause overrides the collation of an expression. It is appended to the expression it applies to. Expression, collate, collation. Where collation is a possibly schema qualified identifier. The collate clause binds tighter than the operators. Parentheses can be used where necessary. If no collation is explicitly specified, the database system either derives a collation from the columns invoked in the expression, or it defaults to the default collation of the database if no column is involved in the expression. Two common uses of collate clause are overriding the sort order and order by clause. And overriding the collation of a function has that locale sensitive results. For example, select star from table where A is greater than foo, collate C. Note that in the latter case, collate clause is attached to an input argument of the operator we wish to affect. It does not matter which argument of the operator or function call the collate clause is attached to, because the collation that is applied by the operator or the function is derived by considering all arguments, and an explicit collate clause will override the collation of all other arguments. Attaching non-matching collate clauses to more than one argument, however, is an error. For more details, see section 24.2. Thus, this gives the same results as the previous example. Select star from table where collate C greater than foo, but this is an error. Select star from table where A greater than foo, collate C, because it attempts to apply collation to the result of the greater than operator, which is of the non-collatable data type boolean. Scalable subqueries. A scalable subquery is an ordinary select clause, a select query in parentheses that returns exactly one row with one column. See chapter 7. The select query is executed and the single return value is used in the surrounding value expression. It is an error to use the query that returns more than one row or more than one column as a scalar subquery. But if during a particular execution the subquery returns no rows, there is no error. The scalar result is taken to be null. The subquery can refer to the variables from the surrounding query, which will act as constants during any one evaluation of the subquery. So array constructors. Select array. Nice. By default, the array element type is the common type of member expressions, determined by using the same rules as for union or case constructs. You can override this by explicitly casting the array constructor of the desired type. For example, select array 1 to 22.7 integer. Is this okay? Nice. Gives an integer array. This has the same effect as casting each expression to the array element individually. For more on casting, see section 4.2.9. Multidimensional array values can be built by nesting array constructors in the inner constructors. This has the same effect as casting each expression to the array element type individually. For more on casting, see section 4.2.9. Multidimensional array values can be built by nesting array constructors. In the inner constructors, the keyword array can be omitted. For example, these produce the same result. Select array, array of 1, 2, array of 3, 4, array. Select array of 1, 1, 2, 3, 4. That makes sense. Since multidimensional arrays must be rectangular, inner constructors at the same level must produce subarrays of identical dimensions. Any type applied to the outer array constructor propagates automatically to all inner constructors. Multidimensional array constructor elements can be anything yielding an array of the proper kind, not only a subarray construct. For example, create table array f1 of integer, f2 of integer, insert into arrays or array values. Okay. Values, select array of f1, f2 of You can construct an empty array, but since it's impossible to have an array of no type, you must explicitly cast your empty array to the desired type. It is also possible to construct an array from the results of a subquery. In this form, the array constructor is written with the keyword array followed by a parenthesized, not bracketed, subquery. Select array, select old from pgproc, where proc name where select array 1 I star 2 from generate series 1 of 5 as a of 5. A of I. The subquery must return a single column. If the subquery's output column is of a non-array type, the resulting one-dimensional array will have an element for each row in the subquery result with an element type matching that of the subquery's output column. If the subquery's output column is of an array type, the result will be an array of the same type but of a higher dimension. In this case, all the subquery rows must yield arrays of identical dimensionality, else the result would not be rectangular. The subscripts of an array value built with array always begin with 1. For more information about arrays, see 8.5. Row constructors. So a row constructor is an expression that builds a row value, also called a composite value, using values for its member. This is The keyword row is optional when there are more than one expression in the list. A row constructor can include the syntax row value dot star, which will be expanded to a list of elements of the row value, just as it occurs when this star syntax is used in the top layer of a select list. Before Postgres 8.2, the star syntax was not expanded in row constructors, so that writing row t star created two field values whose first field was another row value. The new behavior is usually more useful. If you need the old behavior of nested rows, write the inner row value without the dot star. Instance t, 42. By default, the value created by a row expression is of an anonymous record type. If necessary, it can be cast or named composite type, either the row type of a table or a composite type created with create type as. An explicit cast may be needed to avoid ambiguity. For example, create table might do f1 int, f2 float, f3 text. Create table get f1, my table returns int as select thing. No cast required. Create type my row as f1 int f2 text f3. This is like a name tuple. Cast a row, indicate which function. All. Could not choose best candidate function. You might need to nice. Why is this giving an error? Row constructors can be used to build composite values in a to be stored in a composite type table column, or to be passed to a function that accepts a composite parameter. Also, it is possible to compare two row values or test a value with is null or is not null. For example, select row is equal to nice. We don't have a table as such. There's no table expression value rules. Okay. The order of evaluation of sub-expressions is not defined. In particular, the inputs of an operator or function are not necessarily evaluated left to right or in any fixed order. Furthermore, if the result of an expression can be determined by evaluating only some parts of it, then other expressions might not be evaluated at all. Select true or some func. True func1 would probably not be called at all. The same would be the case if one wrote select some func or true. Note that this is not the same as left to right short circuiting or Boolean operators that is found in some programming languages. As a consequence, it is unwise to use functions with side effects as complex expressions. It is particularly dangerous to rely on side effects or evaluation order in where or having clauses, and since those clauses are extensively reprocessed as part of developing an execution plan. Boolean expressions and or not combinations in those clauses can be reorganized in any manner allowed by the laws of Boolean algebra. When it is essential to force evaluation order, a case construct can be used. For example, this is an untrustworthy way of trying to avoid division by zero in a where clause. Okay, this is a bit interesting because in Python, if you have false and true, like false and some heavy function that is true, you definitely know that it will not execute that heavy function just because there is a false here, and it is an and. In the case of an or, if there is a true or a heavy function here, since this is true, we don't care about this part, so it would not even bother evolving. So that is what is called short circuiting of Boolean operators. That's, you learn something every day. A case construct used in this fashion, right? So this is saying, like, when it is essential to force evaluation order, a case construct can be used. For example, this is an untrustworthy way of trying to avoid division by zero in a where clause. Select something where x greater than 0 and y by x is greater than 1.5, but this is safe. Select something where case x greater than 0, then y by x. A case construct can be used. For example, this is an untrustworthy way of trying to avoid division by 0 in a where clause. Select something where x greater than 0 and y by x is greater than 1.5, but select something where case when x greater than 0, then y by x greater than 1.5, else false n. A case construct used in this fashion will defeat optimization attempts, so should not only be done when necessary. For example, it would be better to sidestep the problem by writing y greater than 1.5 start x instead. Case is not a cure-all for all such issues. However, one limitation of the technique illustrated above is that it does not prevent early evaluation of constant sub-expressions, as described in section 38.7. Functions and operators marked immutable can be evaluated when the query is planned rather than when it is executed. Thus, for example, select case when x greater than 0, then x greater then x else. Wait, what? Is likely to result in a division by 0 failure due to the planner trying to simplify the constant sub-expression. even if every row has x greater than 0. Yeah, because it would try evaluating this, since it's a constant sum expression. Interesting. While that particular example might seem silly, related cases that don't obviously involve constants can occur in queries executed within functions, since the values of function arguments and local arguments can be inserted into queries as constants for planning purposes. Within PGSQL functions, for example, within PGSQL functions, for example, using an if-then-else statement to protect a risky computation is much safer than just nesting it in a case expression. Another limitation of the same kind is that a case cannot prevent evaluation of an aggregate expression contained within it, because aggregate expressions are computed before other expressions in a select list or having clause are considered. For example, the following query can cause a division by 0 error despite seemingly having protected against it. Select case when when min employees greater than 0, then average expenses by employees end from the min and average aggregates are computed concurrently over all the input rows. So if any row has employees equal to 0, the division by 0 error will occur before there is an opportunity to test the results of min. Instead, use a where or filter clause to prevent problematic input rows from reaching an aggregate function in the first place. Calling functions. This is a short function. This is a short chapter. Great. That was yeah. PostgreSQL allows functions that have name parameters to be called using either positional or name notation. Name notation is especially useful for functions that have a large number of parameters, since it makes the associations between parameters and actual arguments more explicit and reliable. In positional notation, a function call is written with its argument values in the same order as they are defined in the function notation. In name notation, the arguments are matched to the function parameters by name and can be written in any order. For each notation, also consider the effect of function argument types documented in section 10.3. In either notation, parameters that have default values given in the function declaration need not be written in the call at all, but this is particularly useful in the name notation since any combination of parameters can be omitted, whereas in positional notation, parameters can only be omitted from right to left. Postgres also supports mixed notation, which combines positional and name notation. In this case, positional parameters are written first and name parameters appear after them. The following examples will illustrate the usage of all three notations using the following function definition. Create function, concat lower or upper, A text, B text, uppercase boolean, default false. Returns text as, this is the function definition. Select case when $3 function concat or lower has two mandatory parameters, A and B. Additionally, there is one optional parameter, uppercase, which defaults to false. A and B inputs will be concatenated and forced to either upper or lowercase depending on the uppercase parameter. The default the remaining details of this function definition are not important here. See chapter 38 for more information. Using positional notation, select concat lower or upper, hello world, true. Concat lower or upper, hello world. That's what you get. Select lower or upper, hello. If you just give this, it will give you a lowercase. Here the uppercase parameters is omitted so that it receives its default value of false. In name notation, you copy this, or you use the arrow syntax. You say A is hello, B is world. What about mixed? I'm going to say nice. If I say A, that also works. Great. You also have mixed notation. Named and mixed notation calls currently cannot be used when calling an aggregate function, but they do work when an aggregate function is used as a window function. Data definition. Chapter 5. Data definition. Let's see how many. So I'm hoping to have a soft stop at around 1 p.m., which is an hour from now. data definition, data manipulation, queries, data types, functions and operators, type conversion, indices, full text search, concurrency control, performance tips, parallel query. I'm hoping I have enough time to reach this point, but I think I might not be, for the sake of completion. I might have to do this over the next weekend as well, because I do want to finish everything. Cool. Oops. So I paused, or am I recording? Yeah. Each column has a data type. The data type constrains the set of possible values that can be assigned, and assign semantics to the data stored in the column so that it can be used for computations. For instance, a column declared to be of a numerical type will not accept arbitrary text strings, and the data stored in such a column can be used for mathematical computation. By contrast, a column declared to be of a character string type will accept almost any kind of data, but it does not lend itself to mathematical calculations. All the other operations such as concatenation are available. Postgres includes a sizable set of built-in data types that fit many applications. Users can also define their own data types. Most built-in data types have obvious names and semantics, so we defer a detailed explanation to Chapter 8. Some of the frequently used data types are integer for whole numbers, numeric for possibly fractional numbers, text for character strings, date for dates, time for time of day values, and timestamp for values containing both data and time. To create a table, you must use the aptly named create table command. In this command, you will at least specify this thing. So you have create table, the name of the token for the table, the name of the column, the data type, the name of the second column, and the data type. This creates a table called first table with 2 columns. Alright. The table and column names follow the identifier syntax. The type names have also identifiers, but there are some exceptions. Note that the column list is comma separated and surrounded by parentheses. Of course, the previous example was heavily contrived. Normally, you would give names to your tables and columns that convey what kind of data they store. So let's look at a more realistic example. Table name, products, product number, integer, the numeric type can store fractional components as would be typical of monetary amounts. Nice. When you create many interrelated tables, it is wise to choose a consistent naming pattern for tables and columns. For instance, there is a choice of using singular or plural nouns for table names, both of which are favored by some theorists or the other. Yeah. Usually I prefer plural, by the way. I've always used plural whenever I've created tables for Flask, for example. Like if you have a table that contains details of users, I say it's users. However, when you use something like Postgres, with SQL Alchemy, you use an ORM wrapper. You use the ORM wrapper such as SQL Alchemy or PV or Django ORM or something. Usually the class name is called user because it corresponds to a single row. Like when you get user.query.all or something, you get, or first you say user.query.first, you get one user's data. So it makes more sense to call that class user instead of users. But what all these ORM wrappers IntelliJ do, if you do not specify explicitly what the column name should be, they will choose the lowercase. Like if it is uppercase user, it will make the table name just user with a lowercase u. So instead, I explicitly always name my tables to be plurals. So this is especially useful when you have stuff like a plural which has IES instead of saying this thing. So that is always easier. Cool. If you no longer need a table, you can remove it using the drop table command. For example, drop table this makes sense. I'll put both of these. Yes. It removed two tables. Attempting to drop a table that does not exist is an error. Nevertheless, it is common in SQL files to unconditionally try to drop each table before creating it, ignoring any error messages, so that the script works whether or not the table exists. If you like, you can use drop table if exists period to avoid the error messages, but this is not standard SQL. I did not know this. I always assumed drop table if exists was a real thing. If you need to modify a table that already exists, see section 5.6. With the tools discussed so far, you can create fully functional tables. The remainder of this chapter is concerned with adding features to table definition to ensure data integrity, security, or convenience. Let's see if you want to add data. Let's add data. Let's go to chapter 6. You can create data, insert. Now let's go back. Let's do this in order. Default values. A column can be assigned a default value. When a new row is created and no values are specified for some of the columns, those columns will be filled with their explicit with their respective default values. A data manipulation command can also request explicitly that a column can be set to its default value without having to know what that value is. If no default value is declared explicitly, the default value is the null value. This usually makes sense because a null value can be considered to represent unknown data. In a table definition, default values are listed after the column data type. For example, create table products, product non integer, name text, price numeric, default 9. Okay, let's try this. Okay, that worked. The default value can be an expression which will be evaluated whenever the default value is inserted, not when the table is created. A common example for a timestamp column to have a default of current timestamp so that it gets set to the time of row insertion. Another common example is generating a serial number for each row. In PostgreSQL, this is typically done by something like create table products, product number integer, default, next value, products, product no sequence. Next value, this arrangement is sufficiently common that there is a special shorthand for it. Serial. The serial shorthand is discussed further. So this is like a increment. Just have a serial increment here. Generated columns. A generated column is a special column that is always computed from other columns. Thus, it is for columns which what a view is for tables. So you have height. Let's create something. Create table rectangle, height centimeter numeric, width centimeter numeric, area generated always as height centimeter, start width centimeter, stored perimeter generated always as height centimeter, start to plus width centimeter, start to stored. What happened? What am I missing? I didn't specify the data type. Okay, insert into rectangle 1020. Select the star from rectangle. Nice. Oh, this is good. That's really good. So this is calculated on right. But let's say drop table rectangle. Yes. I was hoping I could calculate on demand. Stored, generated. It's called generated. Yeah, I'm not too bothered by this right now. I'm going to look into this later. Anyway, a generated column cannot be written to directly. In insert or update commands, a view cannot be specified for a generated column, but the keyword default may be specified. Consider the differences between a column with a default and a generated column. The column default is evaluated once when the row is first inserted. If no other row or value is provided, a generated column is updated whenever the row changes and cannot be overridden. A column default may not refer to other columns of the table. A generation expression would normally do so. A column default can use volatile functions, for example random, or functions referring to the current time. This is not allowed for generated columns. Several restrictions apply to the definition of generated columns in tables involving generated columns. A generation expression can only use immutable functions, cannot use subqueries or reference anything other than the current row in any way. A generation expression cannot reference another generated column. A generated expression cannot reference a system column, cannot have a column default or an identity definition, cannot be part of a partition key. Foreign tables can have generated columns. Create foreign table for details. For inheritance, if a parent column is a generated column, a child must also be a generated column using the same expression. In the definition of the child, leave off the generated clause as it will be copied from the user. In the case of multiple inheritance, if one parent column is a generated column, then all parent columns must be generated columns and with the same expression. If a parent column is not a generated column, a child column may be defined to be a generated column or not. Additional considerations: maintain access privileges separately from the underlying base, so it is possible to arrange it so that a particular row can read from a generated column but not from the underlying base columns. Generated columns are conceptually updated after before triggers have run. Therefore, changes made to base columns in a before trigger will be reflected in generated columns. But conversely, it is not allowed to access generated columns in before triggers. Constraints. Data types are a way to limit the kind of data that can be stored in a table. For many applications, however, the constraint they provide is too coarse. For example, a column containing a product price should probably only accept positive values, but there is no standard data type that accepts only positive numbers. Another issue is that you might want to constrain column data with respect to other columns and rows. For example, in a table containing product information, there should be only one row for each product number. To that end, SQL allows you to define constraints on columns and tables. Constraints give you as much control over the data in your tables as you wish. If a user attempts to store data in a column that would violate a constraint, an error is raised. This applies even if the value came from the default value definition. Nice. Create table product. Table products. Insert into products values 10 something this needs to be a token. Nice. Nice. You can also have the constraint definition comes after the data type. This structure has the default value definitions. Data values and constraints can be listed in any order. A constraint, check constraint consists of the word check followed by expression in parentheses. The check constant expression should involve the column thus constrained, otherwise the constraint would not make too much sense. You can also give the constraint a separate name. This clarifies error messages and allows you to refer to the drop-in constraint when you need to change it. The syntax is drop table products, yes. So you're saying you wanted to have a positive price. Positive underscore price. Nice. To simplify, to specify a name constraint, use the keyword constraint followed by an identifier, followed by an identifier. One moment. Yeah. Cool. So to specify a name constraint, use the keyword constraint followed by identifier. I've done all this. Yeah. Create table products, product, no integer, name, text, price, numeric, check. I mean, discounted price, numeric check, discounted price greater than 0, check price greater than discounted price. First two constraints should be familiar. let's see, the third one uses a new syntax. You have two checks here. You check 1 and check 2. It is not attached to a particular column. Which one? The third one. Instead, oh wait, I did not notice that this was in a separate line. I thought it was attached to this. This is interesting. Drop table products. Yes. Insert into products value. Oh, no. Product number 1. Toothbrush. Price is say 30. Discounted price is 10. Let's say I make this 100. Nice. This what if you fail more than one check? Let's say I have a negative. It failed constraint product check, which was products violates check constraint products underscore check. Well, I think that is the last one. The first two constraints are column constraints, whereas the third one is a table constraint because it is written separately from any one column definition. Column constraints can also be written as table constraints, while the reverse is not necessarily possible, since a column constraint is supposed to refer only to the column it is attached to. Postgres doesn't enforce that rule, but you should follow it if you want your table definitions to work with other database systems. The following example could also be written as create table products, product number, integer. Okay, you have this, or even you can write it as price greater than 0, discounted price. You say an and. Okay, this is interesting. It's a matter of taste. Of course it is. Names can be assigned to table constraints in the same way as table column constraints. Create table products. You have an integer. You have product number, name, price. Check. Yeah, obviously you have the constraint valid discount. Yeah, that would have been better than saying products underscore check, because this is very ambiguous. It should be noted that the check constraint is satisfied if the check expression evaluates true or the null value. Most expression will evaluate to null if any operand is null. They will not prevent null values in the constraint column. To ensure that a column does not contain null values, the not null constraint described in the next section can be used. Postgres does not support check constraints that reference table data other than the new or updated row being checked. When a check constraint that violates this rule may appear to work in simple tests, it cannot guarantee that the database will not reach a state in which the constraint condition is false due to subsequent changes of other rows involved. This would cause a database dump and reload to fail. The reload could even fail when the complete database state is consistent with the constraint due to rows not being loaded in any order that will satisfy the constraint. If possible, use unique, exclude, or foreign key constraints to express cross-row and cross-table restrictions. If what you desire is a one-time check against other rows or at row assertion, rather than continuously maintain consistency guarantee, a custom trigger can be used to implement that. This approach avoids the dump reload problem because PG dump does not reinstall triggers until after reloading data, so that the check will not be enforced during a dump reload. Note: Postgres assumes check constraints conditions are immutable, that is, they will always give the same result for the same input row. This assumption is what justifies examining check constraints only when the rows are inserted or updated, and not at other times. The warning above about not referencing other table data is a really special case of this restriction. Yeah, because the other table could be changing. So, an example of a common way to break this assumption is to reference a user-defined function in a check expression and then change the behavior of that function. Postgres does not allow that, but it will not notice if there are rows in the table that now violate the check constraints. That would cause a subsequent database dump and reload to fail. The recommended way to handle such a change is to drop the constraint, either using alter table, adjust the function definition, and re-add the constraint, thereby rechecking it against all table rows. Not null constraints. A not null constraint simply specifies that a column must not assume the null value. A syntax example is create table products. You have this. A not null constraint is always written as a column constraint. A not null constraint is functionally equivalent to creating a check constraint. Check, column is not null. But in PostgreSQL, creating an explicit not null constraint is more efficient. The drawback is that you cannot give explicit names to not null constraints created this way. Of course, a column can have more than one constraint. Just write the constraint one after another. Create table constraints. Product number, integer, not null. Name, text, not null. Price, numeric, not null. Check, price greater than 0. The order does not matter. It does not necessarily determine in which order the constraints are checked. That is very interesting. So if it is null, this will be true, but then it is not null, so it will fail. Yeah. The not null constraint has an inverse, the null constraint. This does not mean that the column must be null, which would surely be useless. Instead, this simply selects the default behavior that the column might be null. The null constraint is not present in SQL standard and should not be used in portable applications. It was added to Postgres to be compatible with some other database systems. Some users, however, like it because it makes it easy to toggle the constraint in a script file. For example, you could start with null, 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 and insert the not keyword where desired. In most database systems, the majority of columns should be marked not null. Unique constraints. Unique constraints ensure that the data contained in a column or a group of columns is unique among all rows of the table. The syntax is create table, yada yada. Give me a moment. When written, yeah, you just say this is unique and you cannot, there's a product ID. So you can also say this. So let's say drop table products, insert into tables. So that is not discounted price, violates unique constraints. Drop table, yes. Print product number should be unique. Yeah, nice. Actually, never thought about naming this. Sure, product number should be unique. That's a nice way of doing it. This is much easier than adding comments. Someone once told me he doesn't like using ORMs, like the ORM wrappers. I think I see a reason why. I wouldn't know how to do this in SQL Alchemy, for example. I'm pretty sure it should be possible, but this is more interesting. This is really interesting. This is good. To define a unique constraint for a group of columns, write it as a table constraint with the column names separated by commas. So yeah, this is far better than saying this thing. So you just say create table example. Great, A and C are this thing. So insert into example values 10, 10, 10. See? 10, 10, 1, right? So yeah, this is like a star. So it says that sorry, select star from change the word example. See, yeah, okay. So the combination of these two should be unique. So that makes sense. Combination values is unique accordingly. I should have read the next line. Though any one of these columns need not be, and ordinarily isn't unique. So you can assign your own name for unique constraint. This is what I saw. Adding a unique constraint will automatically create a unique B-tree index on the column and a group of columns listed in the constraint. A uniqueness restriction covering only some rows cannot be written as a unique constraint, but it is possible to enforce such a restriction by creating a unique partial index. I'm out of water. So let me go get some. In general, a unique constraint is violated if there is more than one row in the table where the values of all columns included in the constraint are equal. However, two null values are never considered equal in this comparison. This means that even in the presence of a unique constraint, it is possible to store duplicate values that contain a null value in at least one of the constraint columns. This behavior conforms to the SQL standard. But we have heard that other SQL databases might not follow this rule. So be careful when developing applications that are intended to be portable. Man. This would be really interesting to build. Like, so far, whenever I've developed like a web API, whatever, a CRUD app, essentially whatever is a CRUD app, I've been using Postgres as my database of choice. If not, I fall back on SQLite. I don't really touch MariaDB or MySQL anymore. I hope never to touch MySQL anymore. But I mean, I understand there will be requirements where people have to use MySQL. And this is interesting. While this does teach you a lot, as long as you stick to the SQL standard, you should hope that you'll be safe. But this is alarming that you have other databases that might not follow this rule. Like, yeah, so your mileage, it's just you saying your mileage may vary. One of the reasons why people like Postgres is, even though it has additional stuff, it still conforms to the standard. It has whatever the standard has, it has, and above that it has some other stuff which you may or may not choose to use, which might not be the same for others. So, primary keys. Where am I? Primary key, foreign key, exclusion constraints. Let me go get some water before I start the primary keys section. goofed. I forgot to record the last half hour. But that's fine. I just went through some simple sections. I just went through the this thing, this section. This was fairly simple, so I don't really need to re-record this. That would be tiresome. Yeah. But great. I am going to break for lunch. I'll be back by, worst case I should be back by 3. So I will more or less. I'll go for around 100.